exponential functions and exponential equations. Before introducing exponential functions and exponential equations, let's start with some properties of exponents. If we have a raised to power m times a raised to power n, I mean same base, where m and n are constants, then we can simplify this by writing a raised to power m plus n. So when we multiply, we add the powers or exponents. For example, if we have 2 to the power 3 times 2 to the power negative 1, this is 2 to the power 3 plus negative 1, and that is 2 to the power 2, which is equal to 4. And if we have division, a to the power m divided by a to the power n, then we write a, the base, and then find the difference between m and n. So the power of the numerator minus the power of the denominator. And as you may notice here, we have the same base. The base is a. For example, if we have 3 to the power 4 over 3 to the power 2, we write 3, the base, and then power of the numerator minus power of the denominator, and that is 3 squared, which is equal to 9. If we have a raised to power m and then raised to the power n, when we raise some value from power to another power, we multiply the powers. So if we have 2 to the power 3 raised to power 2, then this is 2 to the power 3 times 2, which is equal to 2 to the power 6, and this is equal to 64. If we have a raised to power m over n, now m over n is a fraction. This is the exponent. We want to rewrite this expression or this number a to the power m over n as a radical. So we write it this way: a to the power m under the nth root. So this is the inner power, and this is the index of the root. The index of the root is the number that's written here. When the index is 2, we don't need to write it because that's the smallest index for the square root. This is square root. We don't write the index here because that's the smallest radical. And so, for example, if we have 4 to the power 3 halves, then we can write this as 4 to the power 3, this is the inner value, the inner exponent, over the index. The index is 2, but we don't need to write 2. So this is square root of 64, which is equal to 8. Now, if we have a negative power, a raised to negative n, then we can bring this down to the numerator, and the power becomes positive, as you can see here. For example, 3 to the power negative 2 can be written as 1 over 3 squared, and that's 1 over 9. And now one of the most important properties of exponents is the following, and this actually helps us in solving many exponential equations, as we'll see later in this lecture. So if we have a raised to power m equals a to the power n, then if the base is the same, the power, and they are equal, then the powers should be the same. So m is equal to n. For example, 2 to the power x plus 1 equals 2 to the power x. Since the base is the same, then the powers or exponents should be the same. We modify this problem. Let me write 2x plus 1, the power of the first 2, and x is the power of the second 2. So this is 2x plus 1 equals x, and then we solve this let's start by solving it by grouping x. 2x minus x is x, plus 1 equals 0, and then we subtract 1, we get x equals -1. That's the solution. Now if we want to check your answer, we just substitute -1 here. So 2 times -1 is -2, plus 1 is -1. Substitute -1 here, you get 2 to the power -1, and that means the left hand side is equal to the right hand side. Now what is the exponential function? Exponential function is a function that can be written in the form f of x equals a to the power x. The base is constant. The base is constant. And the power is a variable or a function or a variable. So this is different from the polynomials. If you remember, from polynomials we used to deal with terms like this. Now the base is the variable and the power is constant for polynomials. As you can see here, the base is variable and the power is constant. But for exponential function, the base is constant and the power is the variable or a function of x. And the restriction here are a should be greater than 0 and a is not equal to 1. And as we've seen from the video about basic functions, if we have f of x equals 2 to the power x, then we can graph it. The graph of the function looks like this, the red curve. For example, if we have f of x equals 2 to the power x plus 3, now what is the basic function here? The basic function is 2 to the power x, but we have 3 added to the variable, not to the whole expression. It's not here. If it's here, then we add 3 to the whole expression, and that means we make shift up to by 3 units. But here, for this example, 3 is added to the variable x. So since it's added to the variable, we shift to the opposite side. I mean, if we add 3, we shift the basic function 2 to the x 3 units to the left. So let's start by graphing 2 to the x. This is 2 to the x, and we determine some points. Let's determine this point 0, 1, and let's determine the point 1 and 2 here. Now it's better to choose 3 to 5 points, but for this function, since it's simple, we can realize the shape by just choosing 2 points. So now we need to make a shift to the left 3 steps. So this becomes now we subtract 3 from the x coordinate of each point. So let's subtract 3 from 1. When we have 1, we subtract 3, we get -2. So we have -2, the point 1, 2 becomes -2 and 2, same height. And the other point 0, 0, 1, we need to subtract 3 from 0. It becomes -3 and the height is 1. So this is -3 and the height is 1, and then the graph looks like this. Now what is the y-intercept? The y-intercept is, by just substituting x equals 0, we get 2 to the power 0 plus 3, which is 2 to the power 3, that's equal to 8. So the graph intersects the y-axis at 0, 8. So So this is a graph of 2 to the power x plus 3. And you can apply this method on different functions and different translations of the basic exponential function. Now, how to solve equations. Let's take some examples. For example, if we have 2 to the power x equals 4, we want to solve this equation. So in this case, we need to get common base. So this can be written as 2 squared. And this is 2 to the power x. The base is the same, so the power should be the same. So that means x equals 2. Let's take another example. Now, if you want to check your answer, all you need to do is to substitute x equals 2 here. So let's take another example. For example, if we have 1/6 raised to the power x equals 36, then you need to solve for x. So let's bring this 6 up here. So this becomes 6 to the power negative 1 when we bring it up. If you remember, 1 over or x to the power negative n, this is 1 over x to the power n. So 1 over 6, if we bring this up here, it becomes 6 to the power negative 1. So 6 to the power negative 1 raised to the power x is 36. So this is 6 to the power negative x equals 36. And then we need to get common or same base. So 36 is 6 squared. And then since the base is the same, the power should be the same. So negative x equals 2. That means x equals negative 2. You can check your answer by plugging negative 2 into the original equation. Let's take another example. If we have x raised to the power 4/3 equals 81, we want to solve this. In this case, we can solve this in different ways. So let's first rewrite this using radicals. So x to the power 4, this is cube root of x to the 4th, equals 81. And then let's raise both sides to the power 4. So we get to the power 3, sorry. So we get this cancelled, and we have x to the 4th equals 81 to the power 3. And then we take the 4th root of both sides. So x equals plus or minus the 4th root of 81 cubed. And this is plus or minus 4th root of 27. Let me write it this way. 81 is 3 cubed, 3 to the power 4, raised to the power 3. So this is plus or minus the 4th root of 3 to the power 12. And then this is plus or minus 3 to the power 12 over 4. And that is plus or minus 3 to the power 3, which is equal to plus or minus 27. So we have two solutions for this equation. Or we can solve it this way. So we have x to the 4/3 equals 81. And then we can rewrite it using the radicals as x to the 4th cube root. And then the right hand side is 3 to the 4th and then we can take the fourth root on each side. So we get the fourth root of cube root x to the fourth, 3 to the fourth. We can cancel these. We get cube root x equals 3. And then we can raise to both sides to the power 3. So we can cancel these, and we get, and actually here, since we took the fourth root, we have plus or minus, that's even root. So we have plus or minus here. So this is x equals plus or minus 27. So there are different ways, but all of these methods or ways are very similar. Let's take another example. If we have 2 to the power x plus 4 equals 8 to the power x minus 6, we want to solve this equation. So we try to get same base. So this is 8, can be written as 2 to some power. So this is 2 to the power 3, or raised to power x minus 6. And on the left hand side we still have 2 to the power x plus 4. Now this is 2 to the power x plus 4 equals. Now when we raise from this power to this power, we multiply the powers. So this is 2 to the power 3 times x minus 6. So 2 to the power x plus 4 equals 2 to the power 3x minus 18. So we distribute the 3. And then we have, as we can see, we have same base. So the powers should be the same. That should be equal. So x plus 4 equals 3x minus 18. And then we subtract x from both sides to get 4 equals 3x minus x is 2x minus 18. And then we add 18 to both sides because we are solving for x. So this is 22 equals 2x. That means x dividing both sides by 2, x equals 11. And there are many problems or examples on this, on solving exponential equations. This is our last example. As you can see, we want to convert to get same base. So 16 can be written as 2 to the power 4, and the left hand side is still 2 to the power 2x minus 3. We have same base, so the power should be the same. 2x minus 3 equals 4, and then we solve for x. So we add 3, we get 2x equals 7, and that means x equals 7 halves. And we can apply this for different problems. Let's try compound interest problem. The compound interest is given by a equals p times 1 plus r over m, or raised to the power mt. What do we mean by these symbols? A means the accumulated amount, or sometimes called future value, and p is the present value, or sometimes called the principal value. and R is the rate, interest rate. M is number of convergent periods. And T is time in years. So let's take an example. For example, suppose $1,000. $1,000 is deposited in an account paying 4% interest per year, compounded quarterly. Quarterly, that means 4 times a year. First, we want to find the amount in the account after 10 years with no withdrawals. Okay, so in this case we apply the formula directly. A is the future amount, because we are asked to find the future amount after 10 years, so that means future amount. So A equals, what is the principal value? We deposited 1,000 times 1 plus R. What is R? R in this case is 4%, so we write it as 0.04 over M. How many convergent periods? We have 4 convergent periods. This is M equals 4. Or raised to power M times T. Time in years is 10. So this is 1,000 times 1 plus 0.01 raised to power 40. And using the calculator, we find that this is equal to $1,488.86. Now part B, we want to know how much interest is earned over the 10-year period. So in this case, we subtract the original amount or the principal amount from the accumulated amount. So in this case, we get $488.86. Another example. Becky must pay a lump sum of $6,000 in 5 years. Question 1. What is the present value at 3.1%, interest rate, compounded annually, will grow to $6,000 in 5 years. So in this case, we apply the formula. A equals P times 1 plus R over M, or raised to power MT. So in this case, we are given A, the value accumulated, or the future value. It's 6,000 equals, we are asked to find the present value, which is the principal value. 1 plus R is 0.031, this is R percent, so this is the interest rate, over M. This is compounded annually. Annually, that means M is equal to 1, once a year, or raised to the power mt. M is 1, t time in years, it's 5, so this is t. So let's simplify first. This is p 1.031 raised to power 5, and then to solve for p, we divide both sides by 1.031 to power 5. So p is equal to, using calculator, p is equal to 5,150.60 dollars. Now part B, if only $5,000 is available to deposit now, what is the annual interest rate is necessary for the money to increase to $6,000 in 5 years. So we have same formula, A equals P times 1 plus R over M raised to power MT. Now the accumulated amount is given, it's 6,000. P is given, it's 5,000. This is P, the principal amount, times 1 plus R. R is not given because we're asked to find this R, over M. M in this case is 1 because it's compounded annually, that means M equals 1, raised to power MT. T is 5, so we have 6,000 equals 5,000 times 1 plus R, or raised to the power 5. Now we solve for R, so we need to divide both sides by 5,000 first, and then we get 1 plus R to the power 5 equals 6/5, and then we take the fifth root of both sides, so we cancel this with this to get 1 plus R equals the fifth root of 6/5, and then we subtract 1 from both sides. R is the fifth root of 6/5 minus 1. And using calculator, we find that this can be approximated as 0.0371. Now, if the base of the exponential function, if the base is e, and e is a number, this is approximately 2.71828. It's infinite number, if infinite decimal. And in this case, the function f of x can be given by e to the power x. So the base is e. Now we can solve equations same way. For example, e to the power 5 x minus 1 equals e to the power x. Since the base is the same, that means the powers should be the same. So 5x minus 1 is equal to x. So 4x minus 1 equals 0. Then we add 1. We get 4x equals 1. That means x equals 1/4 by dividing by both sides by 4. Now, logarithmic functions. We talked about logarithmic functions before in the video about basic functions. So, logarithmic functions. For logarithmic functions, logarithmic function is defined as f of x equals log base a or base a log of x, where x is positive and a is not equal to 1. And actually this is equivalent to the exponential form x equals a to the power y, because f of x is y. So those two forms are equivalent. Now let's take an example. We want to solve log base x of 8/27 equals 3. In order to solve this equation, we need to convert it into exponential form. Put it into exponential form. So the exponential form, we start with the base. The base is x, and this is the power 3, because log represents the power, is equal to 8/27. Now we need to work on the right hand side. So right hand side can be written as 2/3 to the power 3 equals x to the power 3, and then we take the cube root of both sides to get x equals 2/3. Let's take another example. Log base 4 of x is equal to 5/2. In order to solve this, we convert it into exponential form. So the base is 4, the power is 5/2 is equal to x, the inner expression or function. So that's x. X equals 4 to the power 5/2, and that's 4 under the square root 4 to the power 5. This is the inner and this is the index. So we can simplify more. We can write this as 4 times 4 is 16 times 16 times 4, and this is 4 times 4 times 2. 16 times 2 is 32. One more example. If we have log base 49 of cube root of 7 equals x, we convert this into exponential form. The base is 49, the power is x equals the cube root of 7. And then we can rewrite, if we look at the base here, it's 7 to the power 1/3. And here 49 can be written as 7 squared raised to power x here. So this is 7 to the power 2x equals 7 to the power 1/3. The base is the same. That means the power must be the same. The powers must be the same. So divide both sides by 2. You get x equals 1/6. 1/6. Now, what is the relationship between exponential function and logarithmic function? If we have f of x equals 2 to the power x and f of x equals log base 2 of x, what is the relationship? Between them. Let's start with the exponential function and try to find the inverse. So we first write it as y equals 2 to the power x, and if you want to remember the steps, you need to revisit the video about inverse functions. And then we interchange x and y, so this is x equals 2 to the power y. And then we solve for y. That means we convert this from exponential form to logarithmic form. So the power here is y equals log base. What is the base? The base is 2, and this is the inner function, or the inner variable, or the inner expression. And then we replace y with f inverse. So this is log base 2 logarithm of x, and as you can see, we obtain the logarithmic function. So what does that mean? That means the logarithmic function is the inverse of the exponential function, and the exponential function is the inverse of the logarithmic function. So we find that the exponential function and the logarithmic function are inverses of each other. Now, if you want to show this graphically, you can graph the two functions on the same graph. So this is x, this is y. The graph of 2 to the x, it looks like this. This is 2 to the x. And the graph of the logarithmic function, this is base 2 log of x. And as you can see, those are symmetric about the axis y equals x. If the the graphs of the two functions are symmetric about the line y equals x, then they are inverses to each other. This is how we prove it graphically. Now let's take an example of logarithmic function. This is log base 2 of x minus 1. Now if we want to graph this function, we look at the basic function. Look for the basic function. What is the basic function? The basic function is log base 2 of x. Now if we graph this, the graph looks like this. This is log base 2 of x. It intersects the x-axis at the point 1, 0. And then, as you can see, we subtracted 1 from the variable, not from the whole logarithmic function. And that means we make shift to the opposite side. If we subtract a number from the variable, we make the shift to the right. And if we add, we make shift to the left. So here we subtracted 1. That means we make shift to the right. Log base 2 of x minus 1, we make shift to the right by 1 step, 1 unit, or 1 step. So this gives us this graph. We need to determine 2 or 3 points here. So this is the first point, 1, 0, and let's choose 2, and if we substitute 2 here, we get log base 2 of 2, and that's equal to 1. So this point here is 2, 1. Now we need to make shift to the right. That means we add 1 unit to the x coordinate of each point. So the point 1, 0 becomes 2, 0. This point here. And the point 2, 1 becomes 3, 1. So this is the graph of log base 2 of x minus 1. Now if we want to find the graph of log base base 2 log of x all minus 1. Here we subtracted 1 from the whole function, logarithmic function. So that means we need to pull everything in that graph down one step. Shift down by one step. So the graph looks like this. If the function, the logarithmic function, looks like this, 1 0, and this is another point at 2, it's 1, at 2 it's 1. So this point is 2 1. Then we make shift down by 1 unit. That means we need to subtract 1 from the y coordinates. So this point becomes 1 and -1, and this point becomes 2 and 0. We subtract 1 from here, and the graph looks like this. So this is base 2 log of x minus 1. Now if I ask you to find the inverse of the function f of x equals log base 2 of x minus 1, then we can apply the general steps for the inverse function, but then we can convert from logarithmic form to exponential form. So first we write it as y equals log base 2 of x minus 1, and then we interchange x and y, and then we convert to the exponential form. So the base is 2, this is the power, and we have here y minus 1, and then we solve for y. So we add 1 to both sides, we get y equals 2 to the power x plus 1, and then y is f inverse of x. Now some properties of logs. Properties of logarithms. We have the following properties. Log base a of x times y. We can distribute log on multiplication, and this gives us log base a log of x plus base a log of y. So the multiplication becomes addition, and we have also the division becomes subtraction. If we have base a log x to the nth, we can bring the power here in front of the log. It becomes n log base a of x. And other properties like base a log of 1 is equal to 0, and actually that's log for any base of 1, this is equal to 0. So log base and log base a of a is equal to 1. And actually we can prove this by converting to exponential form. The base is a and the power is 1 equals a. So a equals a, that means it's correct. And here same thing, the base is a, power is 0 equals 1, and that's correct. Any number raised to power 0 is equal to 1 except 0 itself. Now the sixth property is a to the power log base a of x is equal to x, and base a log of a to the power x is x. Let's take some examples. We have log base 5 of square root 8. We want to find this. So this is log base 5 of 8 to 1/2. So we can bring the power here using property 3. 1/3, 1/2, base 5 log of 8. Now we may be asked to expand some logarithm. If we want to expand this expression, then I mean to write it using several logs, but with the same base, we can first start with the power, or the nth root. This can be written as the power 1 over n, and we have x cubed y to the fifth over z to the power m. This is the first step. And then using property 3, we can bring this in the front of the log. It becomes 1 over n log base a of x cubed y to the fifth over z to the m. And then we can, since we have log of a quotient a over b, or x over y, this is log x minus log y. So 1 over n log base a of the numerator minus log base a of the denominator. And then actually this is property 2. And then this is 1 over n. Now we need to apply, here we have multiplication, so we apply property 1 log base a x to the power 3 plus log base a y to the fifth minus this base a log of z to the m. And then can we simplify more? Yes, we can simplify if by bringing the power down here and this power down here. This is the last step, and actually it comes from property 3. So this is 1 over n 3 log base a of x plus 5 log base a of y minus m log base a of z. Now let's take the example of converse. We want to write some expression, logarithmic expression, as a single log. For example, if we have 1/2 log base a of x plus 3/2 log base a of 2y minus log base a of x squared y, then we need to combine these. We need to write just single log. So let's start from the coefficients. We need to bring them up here. So this becomes log base a of x to 1/2 plus this becomes log base a of 2y all raised to power 3/2 minus log base a of x squared y. And then we take the first two terms. We have addition and we have same base of log, so we can write them as single log of base a, and the addition becomes multiplication of the inner functions minus this function log base a of x squared y. And then we still have two logs, the same base, so we can write them as a single log, and subtraction becomes division using property 2. So this is square root x square root, because this is the index, of 8y cubed. I distributed cube over 2y, and in the denominator we have this here, x squared y. Can we simplify more? Yes, we can simplify more. We can write this as log base a of what? Now we have square root in the numerator, so this is x times 8y cubed. It's 8xy cubed over x squared y. Can we simplify more? Yes. I have log base a. Since we don't have square root for the denominator, we can apply square root, but if we apply square root, we need to multiply the powers by 2. So this becomes x to the power 4, and this becomes y squared. And then since we have same root distributed for the numerator and denominator, we can write them using a single root, square root. And then we simplify the expression inside the square root. So we can cancel x with one of these x's. We can cancel the y squared from these 3 multiplied y's. So we get 8y over x cubed. And actually that's the final answer. Now we have some notation. If we have log base 10 of x, this can be written as log of x. We don't need to write the base. This is called common or usual logarithm. And if we have log base e, the number e of x, we don't need to write log base e. We replace it with ln of x. This is natural log. So if you see ln of x, that means log base e of x. Now the last idea here is what's called change of base theorem. For example, if you have log base a of x, we want to change this base into a new base. Let's call it b. How can we do this? We apply the new base, the base b, and we put here x and here a, and that's it. For example, now where a and b are not equal to 1, a, b, and x are greater than 0. These are just conditions on these quantities. For example, log x. If I want to write it using natural log, we can write this as natural log of x over natural log of 10, because the base here is 10. Or if we have log base 3 of x, we can write this using log base 10 as log of x over log of 3. Now, how to prove this result? The proof is very simple. We can write y equals log base a of x, and then convert this into an exponential function, or to write it using exponential form, x equals a to the y, and then we can take log base b of both sides. So log base b of x equals log base b of a to the y, and then by applying property 3, we can bring this down here. We get log base b of x equals y log base b of a, and then we can solve for y. If we want to solve for y, we divide both sides by log base b of a. So we have y equals base b log x over base b log a, and that gave us this formula. But y is here log or base a log of x.